Hello everyone, this is our second video of Trigonometry short courses series. In the previous one, we have studied trigonometric functions, the most basic and fundamental parts of trigonometry. Now in this video, we will study trigonometric equations and we will learn how to solve them. And this is our agenda. First of all, we will see how trigonometric functions are placed in algebraic equations. And then we will see multi-angle equations and quadratic equations as well. And finally, we will have a lot of examples and problem solving. A trigonometric equation is an equation just like the algebraic ones that contains a trigonometric expression with a variable such as sinus x or cosinus x or whatever it is. The values that satisfy such an equation are its solutions. We mean here the angles, of course, whether in degrees or radians. By the way, there are trigonometric equations that have no solution at all, so this is also possible. When an equation includes multiple angles, the period of the function plays an important role in ensuring that we do not leave out any solutions. There are equations where there is one kind of trigonometric function in the equation, and that function is raised to the first power. So these are called first-degree trigonometric equations. And if the function is quadratic, then that will be second-degree trigonometric equations, and it will be named according to the power of the biggest term in the polynomial representation of the equation. Here you see a very basic first-degree one-angle trigonometric equations. It's 2 times sinus x equals to -1. So it's pretty straightforward. We already have seen this in the previous class, but the general idea is exactly like that. We will of course see the more complicated ones, but the general idea is always like that. So the question will ask what is x in terms of either radians, multiples of pi, or degrees. Usually doesn't matter. Normally in these type of problems you get the answer, you get the ratio, you get the proportion or the numeric value on the right hand, and you will be asked the angle. We have a straightforward recipe for solving these kind of equations. To solve an equation containing a single trigonometric function, the most important to do is to isolate the function on one side of the equation, whether the right side or the left side. But the preferred notation is having the function on the left side and having the numerals on the right side. In the second step, we should use exact values to solve and put the answers in terms of usually radians. If the answer is not an exact value, then we can use the inverse function that we have already seen in the previous course, which are arc functions like arcsinus, arccosinus, arctangent, etc. And we may have to use some calculators if we cannot catch the angles from the results. Another important topic to touch here is the solution range. For a basic statement like sinus x equals a, then a can be between -1 and +1. So the solution here, the result on the right hand of the equation, cannot be smaller than -1 and cannot be larger than +1. This limitation comes from the original definition of sinus function, which we have already seen in the unit circle in the previous course. Similarly, for cosinus x, we have the same range. Cosinus x range from -1 to +1 again, just like sinus. Tangent x is quite different. tangent x equals to a can be any value, any real number for a. So there is no limitation unlike sinus or cosinus. It will be similar for cotangent also. Ranges are important. Usually you can see the range in the question, but it may depend. So if you are dealing with engineering problems, nobody will provide a range, so you have to find out the range yourself. But do not forget, most trigonometric functions have a period of 2 pi, so usually when you add 2 pi to the angle you find, you will get another solution if the range is not limited. So let's evaluate this basic function. 2 times sinus x equals to -1. So first step is to isolate the trigonometric function on one side. This means that sinus x equals to -1 over 2. So here we should figure out where the sinus equals -1 over 2 on the unit circle. And -1 over 2, which translates as -0.5, can be obtained via sinus function on 7 pi over 6 and 11 pi over 6, assuming that we are limited to 2 pi. If we are not limited to 2 pi, then we can add 2 pi to these angles and find an infinite number of solutions. Here on the top figure we see two functions. First one is a very simple one, y equals to 0.5, so it's a straight line and demonstrated with a dashed line on the graph. And the second one is y equals to cosinus x. This function represents a sinusoidal or cosinusoidal signal and has a wave-like visualization on the graph. You see that it ranges its values for y. The variable y ranges from -1 to +1 and visiting 0 in between. And period of the function is 2 pi. So the results start to be identical after 2 pi. So they just repeat over x values of cosinus function, and it will be very, very similar with the sinus function. Cosinus x equals to 0.5, as you can see, has infinitely many solutions for negative infinity, x, and positive infinity. So if we can limit, or if the question limits the range of x, then we will have a finite number of solutions for cosinus x equals 0.5. And now we can observe the second figure below. Here, cosinus x equals 0.5 has two solutions for x between 0 and 2 pi. So this is just one original figure from the collection of wave signals we see above. Let's look at another example. The question asks me that the equation 3 times sinus x minus 2 equals to 5 times sinus x minus 1. Here we have two sinus functions on both hands of the equation. So first step was to isolate the trigonometric function on one side. So we should do that exactly. And the good thing is here we only have one kind of trigonometric function, so it's only sinus function. If we collect sinus functions on one side, what we should do is let's choose left side, but it could also be the right side. Let's choose the left side and continue. We should subtract 5 times sinus x from both hands. Now we get minus 2 sinus x minus 2 equals to minus 1. And if we add 2 for both sides, we will get minus 2 sinus x equals to 1. So it is much more simpler this way. And finally, we get sinus x equals to minus 0.5 when we divide both sides by minus 2. And here we can easily see that the angle whose sinus gives minus 1 over 2 is 30 degrees. If you cannot memorize this, you can easily cheat online or take a look at the unit circle. Unit circle will help. Another example, solve the equation 2 times cos square x plus cos x minus 1 equals to 0, where 0 is smaller than x and which is smaller than 2 pi. So we have a range for the x variable here. And as you see, this example, this equation is not first degree anymore. We have a square. This equation is in a quadratic form. So if we replace cosinus x with an arbitrary temporary variable called t, or whatever you call it, we get 2 times t squared plus t minus 1 equals 0. And in this form, it could be easier for you to solve. What we should do here is to factor the equation. You can either continue with t, which will be more clear for many of you to solve, but in case you don't want, you don't have to. If you factor the given equation, we will get 2 times cosinus x minus 1 times cosinus x plus 1 equals to 0. And here, one or both of these two factors can be 0 to find the solution of the equation. In the first case, if we set 2 times cos x minus 1 to 0, we will get one solution. And in the other case, cosinus x plus 1 equals 0, we will get another solution. So since the equation is quadratic, it's very natural to have more than one solutions for one equation. Here we get 2 times cosinus x equals to 1, which translates as cosinus x is 1 over 2. And another solution is, of course, cosinus x equals to minus 1. And we are already given the solution interval for the angle x, which was 0 to 2 pi. And the solutions in this interval are pi over 3, which is 60 degrees, pi, and 5p over 3. In this example, the equation is 7 times cos theta plus 9 equals to minus 2 cos theta. 7 times cosinus theta plus 9 equals to minus 2 times cosinus theta, so that if we move the right hand side to left hand side to isolate the function, we will get 9 times cosinus theta equals to minus 9, which is directly cosinus theta equals to minus 1. And for theta, we get pi, 3 pi, or 5 pi. So we can derive these solutions because there is no range limit given in the question for the angle theta. And in that case, we can generalize our solutions, like theta equals to pi plus 2n pi, where n is a positive integer. In this example, we have the range interval from 0 up to 2 pi for the angle theta. And the equation is tangent theta over 2 equals to square root 3 over 3. Here, we do not have only theta, but theta over 2 in the tangent function. This is not hard, but we just have to pay attention. Here, not theta, but theta over 2 equals to pi over 6 and 7 pi over 6. And this makes theta pi over 3, which is 60 degrees, and 7 pi over 3. In this example, again we have the same interval from 0 up to 2 pi for the angle x. Cosinus square x plus 2 times cosinus square minus 3 equals to 0. Here again we have a quadratic form for the trigonometric function, and if you feel yourself more comfortable, you can change cosinus x to t and continue factoring with t, and then replacing t with cosinus x again at the end. But of course that's not necessary. This quadratic form can be factored as multiplication of two terms, which are cosinus x plus 3 and cosinus x minus 1. So this multiplication must be 0, since the original quadratic form is equal to 0. In this case, either of or both of these solutions can be 0, and in this way we can get the solutions. If cosinus x plus 3 equals to 0, then we will get cosinus x equals to minus 3 if we subtract 3 from both sides. And cosinus x equals to minus 3 is quite weird. In this case, we don't have a solution for this factor, because it cannot be possible. Think about the unit circle and think about the natural range of the cosinus x function. So range of x is different, and range of cosinus x is different. Do not mix them. Pay attention. A cosinus function for any x angle can have values from minus 1 up to positive 1. So it cannot be minus 2 in the real world. On the other hand, the other term, cosinus x minus 1 equals to 0, may have a solution. If cosinus x minus 1 equals to 0, then cosinus x equals to 1. In this case, we have to find for which angle cosinus x makes 1. And if you take a look at the unit circle, or use your calculator, or if you have already memorized, you will easily get the angle must be 0 to get this result. If you remember the definition of cosinus, it won't be hard to memorize it. As it is the length of the adjacent side over hypotenuse. So even this equation is a quadratic form, an equation of second degree. We only have one solution, which is 0. Here, for the given interval from 0 to 2 pi, the question is sinus 2 times x equals to sinus x, which is an interesting one, but not hard. In this case, we have to use one of the identity relations that we have learned in the previous course. Sinus 2 times x is the double angle identity, and it can be translated as 2 times sinus x times cosinus x equals to sinus x. So if you use this double angle identity, it will be much easier to solve. So in this case, we can divide both hands with sinus x, and we will have cosinus x only on the left side, and on the right side we won't have any trigonometric functions. So this means that we only have 2 times cosinus x equals to 1. And if we continue, cosinus x must be 1 over 2, which is 0.5, and the angle is here trivial. The angle must be pi over 3, which is 60 degrees, or 5 pi over 3. If there was no interval, we could continue adding 2 pi's to the solution and get unlimited number of x values. Let's look at another one. 2 times sinus square x plus 3 times cosinus x minus 3 equals to 0. Here we should use another identity relation using Pythagorean theorem. Sinus square x can be written as 1 minus cosinus square x, as we already learned that sinus square x plus cosinus square x always make 1, and this is independent from the value of the angle x. So if we convert sinus square x using this relation, we get 2 times 1 minus cosinus square x plus 3 times cosinus x minus 3 equals to 0. And the main reason we are doing this is, in this equation, we have 2 different trigonometric functions, sinus and cosinus. So a good thing to do is reducing this variety to only 1. If we have only one trigonometric function, the question will be much more easier. If we make this multiplication with 2, we will get 2 minus 2 times cosinus square x plus 3 times cosinus x minus 3 equals to 0. And in this case, we get minus 2 times cosinus square x plus 3 cosinus x minus 1 equals to 0. And we can also multiply both hands of the equation with minus 1 to just adjust the signs. And here we should factor, because we already solved the problem of having more than one trigonometric functions, but our equation is in quadratic form, so it's a very clever thing to do, factor this equation to get solutions. If we factor it, we get 2 terms, like 2 times cosinus x minus 1 times cosinus x minus 1 equals to 0. So either or both parts could be 0 to get the solution. And if we make 2 times cosinus x minus 1 equals to 0, we get cosinus x equals to 1 over 2, which is 0.5. And in this case, the value could be pi over 3 or 5 pi over 3. And you can replace pi with 180 degrees to find out the degree equivalence. On the other hand, if cosinus x minus 1 equals to 0, cosinus x minus 1 equals to 0, then cosinus x should be positive 1, and this is only true if x is 0 degrees or 2 pi degrees, since we don't have the interval limitations here. Let's repeat the steps. We replace sinus square x with 1 minus cosinus square x just for the sake of having one kind of trigonometric function. Then we distribute 2 inside, which is a trivial part. We combined the terms and multiplied both hands of the function with minus 1 to adjust the sign of the equation, and we factor. Then we set each factor of the equation equal to 0 to find out the solutions. The question asks us solving the equation 5 times sinus x equals to 3 sinus x plus square root 3. In this case, we can collect both sinus functions on, let's say, the left hand of the equation. And we get 5 sinus x minus 3 sinus x equals to 3 sinus x, 3 sinus x plus square root 3, which is 2 sinus x, equals to square root 3. And then we get sinus x equals to square root 3 over 2. We already get sinus x equals to square root 3 over 2, but since the intervals are not given, it could be from 0 degrees to an infinite number of solutions. For the unit circle, for 0 to 2 pi degrees, solutions are only pi over 3, which is 60 degrees, and 2 pi over 3, which is 120 degrees. But if we do not limit the equation, we get pi over 3 plus 2m pi for any integer value of n, and 2 pi over 3 plus 2mp for any integer value of n as the solutions. This is the generalized form of the solutions of this equation when when the angle variable is not limited with values from the unit circle. This short example contains a little trick to pay attention. It asks us to solve the given equation tangent 2 times x equals to square root 3 with the given interval of x between 0, including 0, up to 2 pi, excluding 2 pi. Here we already know which tangent of which angle makes square root 3, and it is pi over 3. But the equation is not tangent x equals to square root 3. It is tangent 2 times x equals to square root 3. So tangent pi over 3 is only 2x, not x itself. So the angle here must be pi over 3 over 2, which is pi over 6. If you remember the previous course, the period of sinus and cosinus functions are 2 pi, but period of tangent and cotangent functions are only pi. So if we didn't have that interval for the x angle, we could write the solution like 2 times x equals to pi over 3 plus n times pi, where n is any integer value to represent the periodic structure of the function and its variable, and which yields x equals to pi over 6 plus m pi over 2 if we divide both sides by 2. In this special case where n equals to 0, x would be pi over 6 plus 0 pi over 2, which is only pi over 6 again. But in the generalized case, if n equals to 1, then we get x equals to pi over 6 plus pi over 2, which equals to pi over 6 plus 3 pi over 6, which is eventually 2 pi over 3. That also translates as 120 degrees. If n equals to 2 for the same equation, then we get x equals to pi over 6 plus 2 pi over 2, which is pi over 6 plus 6 pi over 6, which is eventually 7 pi over 6. And if n equals to 3, x equals to pi over 6 plus 3 pi over 2, which is eventually 5 pi over 3. And for the original interval for x, so here do not confuse the interval for the tangent function, which is the period of tangent function, with the given interval for the angle x. Here we have x from 0 to 2 pi, and in this range we have 4 values for this x angle, which are pi over 6, 2 pi over 3, 7 pi over 6, and 5 pi over 3 from smallest to the largest. If we continue calculation with n equals to 4, then we will get an x value which is larger than 6 pi over 3, which is also larger than 2 pi. Then this result would be out of the question's range, where it stays x is between 0 and 2 pi. This is why we do not continue. But for your calculation in exams, in practices, in engineering problems, you may try to solve the equations for larger values and see if the result is in the given interval or not. Let's look at another example where 4 times cosinus square x minus 3 equals to 0, and the given interval for angle 0 is from angle x is from 0 to 2 pi. Here, if we move 3 to the other side, but by adding 3 to both sides, we get 4 times cosinus square x equals to 3. And this translates as cosinus square x equals to 3 over 4, which yields cosinus x equals to plus or minus square root 3 over 4, which is plus or minus square root 3 over 2. And for the given interval of 0 to 2 pi, we get pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So we get 4 results again for the given interval. If we didn't have that interval, we would have infinite number of alike solutions. Here we have a little different equation. Sinus x times tangent x equals to sinus x, where x is between 0 and 2 pi. Here, a very intuitive solution is dividing both sides by sinus x and getting tangent x equals to 1 as a result. So here it could be easier to find the solution for tangent x, but in this case we will lose some resolution. We will lose the solution where sinus x could be 0. In the cases sinus x equals to 0, then this division could result in a zero division, which is illegal to the known math rules. And we could get only the result for tangent x. So a better thing to do is just moving sinus x to the other side and having sinus x times tangent x minus sinus x equals to 0. In this case, if we get to parentheses for sinus x, the result is sinus x times tangent x minus 1 equals to 0. Here we can solve the equation for both sinus x and tangent x minus 1. And both solutions would give different results. This is why we do not initially divide both hands of the equation by sinus x. Otherwise, we could lose some resolution for this problem. And we could easily omit some of the valid solutions. And in some engineering problems, this causes a huge issue. So before dividing both sides with a variable that can easily be 0, think twice. If we solve the first factor, we will get sinus x equals to 0, and the angles that make sinus function 0 are 0 degrees and pi degrees, which is 180 degrees. Sorry, pi radians, which is 180 degrees. And the other factor is tangent x minus 1 equals to 0. Here we get tangent x equals to 1, and we already know which angles make tangent function 1. And they are pi over 4, which is 45 degrees, and 5 pi over 4. Since we already have a given interval for the angle, which is 0 between 0 and 2 pi, we only get these results, these 4 values for the x that satisfy the above given equation. The solutions are 0, pi over 4, pi, and 5 pi over 4. In this problem, we have cosinus 2x plus sinus x equals to 0. So it's not cosinus x, but cosinus 2 times x in the given interval of 0 to 2 pi. Here we can again use an identity to solve the equation. Cosinus 2x, the double angle, equals to 1 minus 2 times sinus square x. So we can use this identity and add sinus x to find 0. We get 2 times sinus square x minus sinus x minus 1 equals to 0 if we multiply both sides with minus 1. And if we factor this term, we get 2 times sinus x plus 1 multiplied by sinus x minus 1 equals to 0. In one solution, we get 2 times sinus x plus 1 equals to 0, and 2 times sinus x equals to minus 1, and sinus x is minus 1 over 2. And the angles that give minus 1 over 2 are 7p over 6 and 11 pi over 6. And if we look at the second term, which is sinus x minus 1 equals to 0, we get sinus x equals to 1. And I'm sorry about this very little font size, but it says obviously x equals to pi. And since we already know the interval for angle x, the solutions are pi, 7 pi over 6, and 11 pi over 6. The question asks us solving the given equation correct to 4 decimal places for the given interval of x between 0 and 2 pi. The equation is tangent x equals to 3.1044. Here, what should we pay attention to is tangent x is positive in quadrants 1 and 3 only. This is very important to narrow down the possible angles for x. And if we use the reversal functions that we learned in the previous course, which is arctangent function in our case, we will find the solution. Now x equals to reverse of tangent, which is arctangent 3.1044, and the calculator would give us x equals to 1.2592 in the quadrant 1. And in quadrant 3, we should add pi to this x value, and which is roughly 3.159. We will get something around 4.4008. And these two, I mean 1.2592 and 4.4, are our two solutions for this equation in the given interval. Here we have a similar example where sinus x is given as minus 0.32315, and the interval is given as x, the angle, between 0 degrees and 2 pi. So since sinus x is given as negative, we should consider the unit circle and find out that sinus x is negative in quadrants 3 and 4 only, not 1 and 2. So if we continue solving, we will get x equals to arcsinus minus 0.2315. We will get x equals to roughly 0.2336. In quadrant 3, we should add pi to find the value of x in quadrant 3. So x would be 3.3752. In quadrant 4, on the other hand, we should add 2 pi. We should subtract that result from 2 pi. And if we subtract 1.2592 from 2 pi, we will get 6.0496 as the result in quadrant 4. Here we have 4 additional example equations for you to solve. I will not dive deep into details. We already have enough examples here, but please stop the video here and solve the equations and compare your answers with the given solutions here. Our course, the second part of our course is over, and I would like to acknowledge the owner of some of the original owner of some of the slides here. Thanks for listening. The next course will be about the engineering applications of trigonometric functions and relations.